In the next set of videos, we consider discrete Markov chains. And the first video on that is about the Markov property. So Markov property, first we start with the informal definition of Markov property. And that there we see that a stochastic process satisfies the Markov property if the future depends only on the present, not on the past. So basically, the future depends on the present, not on the past. So it means what is going to happen at the next step is determined by what is happening right now. So that is the Markov property, basically. But then the mathematical definition goes like this. Let x naught, x1, xn, and all that be a stochastic process. The Markov property states that probability of xn plus 1 equals x given xn minus 1 up to x naught is equal to probability of xn plus 1 equals x given xn. So the probability is simply that xn plus 1 is equal to x given that xn is already in place. So this means that once the present state xn is known, past states become irrelevant, right? So every step only determines the next step after it, and that's all. So that's the mathematical definition right there. For the intuition part, for a random walk is an example. Next step depends only on current position. Then you have a weather model. Tomorrow depends only on today's weather. And board game. Next move depends only on current position. This is why the Markov property is often called memoryless. So the Markov property has no memory beyond the step exactly before the current one. So we talk about Markov versus non-Markov processes. So we have for a Markov process, this depends on current state only. And for a non-Markov process, you have entire history. So for a non-Markov process, right, you need every information that has preceded this current state. But for a Markov process, you need just the step before this one, like we've been saying. So example, we have a weather model, for instance, and imagine um we have two states. It's either sunny S or rainy R, and we have transition probabilities like this P 0.8, 0.2, 0.4, 0.6. So that's like having SR. It's like 0.8, 0.4. Okay. So it's like P now is this is 0.8, this is 0.4. So SR. So this is 0.2 and this is 0.6. So this simply means the probability that if today is sunny, tomorrow will also be sunny is 0.8. And the probability that if today is sunny, tomorrow will be rainy is 0.2. The probability that if today is rainy, tomorrow will be sunny is 0.4. Probability that if today is rainy, tomorrow will be rainy also is 0.6. That's basically what that transition probability that represents this one we have here. So just like I said, the interpretation is that probability that today is sunny and tomorrow is rainy is 0.2. So sunny, rainy 0.2. Then probability that today is rainy, tomorrow is sunny is 0.4. So that is if today is sunny, then we have that probability rain tomorrow, given that today is sunny, is 0.2. And that's the interpretation like I've given. So then we have a two-step transition. So we compute probability that x2 equals r, given that x naught is s. That means probability raining given it was sunny yesterday, right? Probability tomorrow will be rainy, given that yesterday was today is sunny. So using total probability rather, probability that x2 equals r given x naught equals s is equal to summation of of all x over sr, such that for p probability x2 equals r given that x1 is x, and multiply by probability that x1 equals x given that x naught is s, like that. So in that case now we have probability r given s multiplied by probability s given s on one hand, plus probability r given r plus multiplied by probability r given s. So we get the total probability. So in that case, we then have probability that it is sunny tomorrow because it's when it's raining today is then 0.2 multiplied by 0.8 plus 0.6 times 0.2. So all of that will give us 0.16 plus 0.12, which is 0.28. So here we have so we have the two steps, right? This is x2 given x1 and x1 given x naught. So that's rainy sunny multiplied by sunny sunny, then rainy rainy multiplied by rainy sunny, like that. So that feels like some kind of chain reaction like that. So RS, so to get RS, it's RSSS, then RRRS, like that. So yeah, so based on uh so from here now we get 0.28 for that, right? But we can do a Python code simulation to get that same thing, two-step transition. So 0.28 here tells us about the rainy, sunny situation. So and here we then have we can have some more simulation. You have this here, and then we're going like 10 steps. So, and this one shows sunny, sunny, rainy, 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 sunny, 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 like that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, like that. So we have that. Then talking about transition probabilities now. So transition probability is that probability we already saw, and I try to interpret that. So if you define Pij to be probability xn plus 1 equals j, given that xn equals I, then the transition matrix can then be said to be P equals P11. So P11 means probability xn is equal to 1, given that the probability that xn plus 1 is 1, given that xn is already 1. So that means probability that tomorrow will be 1 if today is already 1. So 1, 2. Probability that tomorrow will be 2 given that today is already 1, and so on and so forth. So that's the transition matrix, or is matrix. I keep mixing that up. Matrix, right? So 15.7, we have the end step transition. The probability of moving in end steps is given as Pn equals P power n. So matrix powers gives future state probabilities. So n talks about the number of steps that we're taking. Then 15.8, we talk about the memoryless property. The Markov property implies that future determines the past. Future is determined by the past, not the present. This, like, okay, I think this is a better way. The present state fully captures all necessary information. So the present state fully captures all necessary information. So the present state determines the future. We don't need all the past information like that. So that's the memoryless property that we only need this point to determine the next point. Every point before this point is irrelevant. Basically, that's the memoryless property right there. Then when Markov property fails, so if probability of xn plus probability xn plus 1, given that given xn comma xn minus 1 and all that is not equal to probability xn plus 1 given xn, then then the process is not Markov. So in essence, we are saying that, so what this would mean is that xn minus 1 matters in this situation, because in the Markov situation, like, right, only xn determines xn plus 1. But if this expression turns out not being equal to that situation, it means that the Markov property actually fails. So example is weather depends on last 2 days instead of just today. So if tomorrow's weather depends on today, then that's Markov. Or if tomorrow's weather depends on the weather today and the weather yesterday, then it's no longer a Markov situation there. So what about converting non-Markov to Markov? Can we convert a non-Markov process to a Markov process? We can redefine the state. Instead of xn, we can say we can use xn comma xn minus 1. That means that what happened yesterday determines what happens today. This expanded state makes the process Markov again, right? So normally it should be what is happening today is going to determine what happens tomorrow. But we can also we can also have determine that what happened yesterday determines what happens today. So an example of that, okay, we have an example generally. So given P is 0.7, 0.3, 0.5, 0.5, an initial state x naught, which is 1, comma 0. So we want to find probability after three steps. So all the possible probabilities after three steps, right? So whatever we decide this to be. So after three steps, what are the probabilities like? So if you simulate that, of course, we end up getting 0.628 and 0.372 after three steps, like that. So yeah, we have that. I'm thinking if I should go for that. Okay, yeah, I mean it's just basic the whole probability thing, right? So we have 1 comma 0 multiplied by for us to get a 1 by 2, 1 row 2 column, right? So we have a 1 row 2 column by 2 2, like that. So multiply the two together in three steps, and we end up having 0.628 and 0.372. So if we talked about the sunny and the rainy thing now, it means that if if this whole state represents sunny, rainy, so after three steps, the probability that the weather will be sunny will be 0.628, while the probability that it will be rainy will be 0.372 in that situation. So in summary, we say that a Markov property means memoryless behavior. That is, only current state matters in determining what happens in the next state. Then it is defined using conditional probability. So that's probability xn plus 1 given xn, right? Then it is defined using conditional probability and it is represented using transition matrices. The future probabilities are computed via matrix powers. So future probabilities are computed using matrix powers. Okay. So, so we have some practice problems. First of all, we have some conceptual questions. Define the Markov property in your own words. Of course, the Markov property just says that the current state determines the next state. To write the mathematical expression of the Markov property using conditional probability. Of course, that would be this that we saw before now. Um, Probability of xn plus 1 given xn minus 1 is basically the same thing as probability xn plus 1 given xn, meaning that this we have no memory of this, so memory lost. We don't need this basically, so it doesn't matter in the scheme of things because only this step matters in determining this step. So that's basically the idea of the Markov property. Then give one real world example of a Markov process. Of course, we've given examples of the weather model and things like that. Then give one example of a process that is not Markov and explain why. Um, okay, I mean, we had an example before that. If we need the yesterday's weather and today's weather to determine tomorrow's weather, that's not Markov any longer, right? So all that. Then basic probability questions. Suppose the process satisfies the Markov property, express this in the simplest form. Of course, if this satisfies the Markov property, that means that we have we have probability x3 given x2, x1, x naught. So if it satisfies Markov, that should be probability x3 given x2, and that's all because all these are lost. So the memory of x1 and x naught are not necessary, basically. So, if probability of xn plus 1 equals j given xn equals I is 0.6, what does this represent? That means probability that xn plus 1 is equal to j given that xn is equal to 1 is 0.6. So probability that the current state determines the next state is 0.6. Then we have a true or false situation here. So probability of xn plus 1 given xn comma xn minus 1 is equal to probability of xn plus 1 given xn always holds for Markov process. Exactly. So that's true. Then for question 9 now, we have this transition matrix. What is P? Probability 1, 2. So this is 1, 2, 1, 2. So probability that 2 happens given that 1 already happened. So that is this is 1, 2, right? This is 1, 2. So that'll be 0.1. All right, because that's 0.1, 0.5, right? Okay. So this is 0.9, 0.1, 0.5, 0.5. So let's say this is 1, 2, 1, 2. This is P, right? So that's is that P? Hope I didn't just make that up. I think that should be P. That's called P. Yeah, it's called P there. Good. So we have that, we have then that probability 1 to 2. So probability that 2 happens after 1 happens is, so this is 1, 1. This is 1, 2 now. This is what we need. So probability 1, 2 is equal to 0.1. Probability 1, 1 is 0.9. Probability 1, 2 is 0.1. So this is what we need. Probability 2, 1 is 0.5. Probability 2, 2 is 0.5 also in like that. Then for the same matrix, what is the probability of staying in state 1? For this matrix now, the probability of staying in state 1 is 0.9. That means for moving from 1 to 1. Verify that each row of a transition matrix sums to 1. Of course, if you have any transition matrix, each row will sum to 1, basically. Then two-step transitions now. So for two-step transitions, you want to compute, so for two-step transitions, you have given 0 0.8, 0 0.2, 0 0.3, 0 0.7. You want to compute probability that x2 is equal to 2, given that x0 is equal to 1. So in that case now, we have to do the kind of rainy, sunny kind of thing we did. So we have x2 given x1. So that will be probability x2 given x1. All right. So we have to do the total sum, the situation we had the other time with the two-step transition. So you want to check that up to finish this up. Uh, so this is what I'm referring to. Um, yeah, this particular one, we have this kind of two-step transition. So x2 is R, x0 is equal to S. So we do RS, SS, then we do RR, RS. Okay, I think I should do that actually. I was trying to avoid it, but that's okay. Um, so RSSS, RR, RS. So that's R given S, right? R given S. That is R given S is R SR. That'll be S. That's moving from S to R. So S to R. That's 0.2 here. Okay. So yeah, I think I want to do this now. So I'd be happy to still refer to that to be very sure. Where is that now? Yes, this. So we have 0 0.8, 0 0.3. So imagine P is 0 0.8, 0 0.3. Okay, no. 0 0.8, 0 0.2, 0 0.3, of course 0 0.7, like this. So that's what we have. So we need P x2 equals 2, x naught equals 1. Okay. So P x2 equals 2 and x naught equals 1. So we do the kind of thing we did with RS the other time. So don't forget this is now this is 1, 2, 1, 2. So probability of 2 given 1, that's what we need there, right? So this is like probability of 2 given 1. That'll be probability of 2 given 1. That'll be probability um okay, now I need to check that up again. I want to be very sure of the flow. Yeah, probability of RS now. RS. So that is 2 given 1. That'll be 2, 1 multiplied by 2 given 1. That'll be 2, 1 multiplied by 1, 1, then 2, 2 multiplied by 2, 1. So this is like RS, SS, RR, RS, okay? RS, SS, RR, RS, SS, RR, RR, SS. I need to confirm that once more. So RS, SS, RR, RS, RS, SS, RS, SS, RR, SS, RS, SS, RR, RS, RR, RS, RSSS. Okay, yeah. So that I just want to follow this now. So probability of 2 given 1 will be probability of um. So this is like RS now. So probability of 2 given 1 would be probability of 2 given 1 probability multiplied by probability of 1 given 1 plus probability of 2 given 2 multiplied by probability of 2 given 1. So RSSS, RRSS. So it's more like a chain rule kind of thing. So let's say RS times SS. So this cancels. So we have RS. Then we can also have RR times RS. So at the end of the day, everything just, so it's more like it's kind of chain rule, right? So that's what we have there. So that's probability 2, 1. So this is like 2, 1 times 1, 1. So it's still 2, 1. Then here we have 2, 2 times 2, 1. So 2 cancels, we still have 2, 1. So overall, we have 2, 1. So now that all of that is in place, then we can fix the values. So we then have this to be probability 2 given 1. So that is okay, this is 2 right here. So probability of 2 given 1. Well, to make it make sense, to avoid confusion, 2 given 1 means probability you move from 1 to 2, then times probability you move from 1 to 1. To avoid confusion, probability 2 given moving to 2, and probability 2 moving to 1. That's what this actually means. Okay, probability 2 moving to 2, and then probability 1 moving to 2. So 2 given 1, that means 1 has happened, then we go to 2. So 2 given 1 is probability 1 moves to 2. 1, 1, 1, 1. 2, 2 is 2, 2. Then 2, 1 is probability that 1 moves to 2. So then we can get everything together. So P12, so this is P12 right here, that's 0.2, 0.2 multiplied by P11, 0.8 plus P22, P22 is 0.7, and P12 is 0.2 again. No, P12, 0.2. Oh, P21. Okay, I think I was wrong with P21. P21 is 0.3. P21 is 0.3. P12 is now 0.2. Let's check again. 1 to 2, 0.2. 1 to... Oh, okay. Uh, we have to be careful. So probability 2 given 1, that's it. That is 1 to 2. That is 0.2. Then 1 to 1 is 0.8. Then 2 to 2 is 0.7. Then 2 to 1 is now 0.3. Okay, I think that first one was good. So 0.2 times 0.8, that's 0.16. 2 times 8 is 16. So 2 decimal places plus 0.21. So all of that will just be 0.37, I believe. 0.37. So that's a two-step thing we are doing there. 0.37 when we add all of that up. Okay, I think with this, I'll leave it to take care of the other uh, practice problems. So I did 12 already. So write the formula for a two-step transition probability using summation. Okay, that still refers to this summation formula I have up here. The one we just did now. So this is the summation formula right now. So that's x2 equals r, given x1 equals x, and multiplied by p, x1 equals x, given x0 equals s. Okay, so try your hands on the problems. For matrix powers, of course, we want to just square that matrix. So compute p squared manually for the matrix above, then simulation and interpretation. So yeah, just try your hands on this. Let's see how all of that goes. With this, I come to the end of this interesting video about Markov property, and which tells us that the current state determines the next state. The state before the current state do not matter in determining the next state. That's why it is called memoryless, right? So try your hands on the questions, of course, and see how well you get the gist. If you have subscribed already, thank you so much. If you haven't subscribed, why not go ahead and subscribe right away? Hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can become a member of the channel by clicking on join. That gives you some special privileges, that you're going to find as you click on join. Like you get to see some videos first and all that. Ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Don't forget to try your hands on the problems that I have given. Till I come your way again, keep doing maths right. Bye.